Okay, so first of all, we're going to look at the z-test. So the z-test uses a sample mean to test for the population mean. It can be used whenever the population standard deviation is known, when the population is distributed normally, or when sample size is large enough to apply sensory limit to error. So we have a sample question here. So based on the question, I've extracted the information. So the population mean is going to be 500 gram. The standard deviation is going to be 10 gram. The sample mean going to be 405 gram, and the total sample going to be 50 bags. So based on those information, we fill out in the GDC, and then you just press OK, and the answer going to be p-value equal to 0.00204. So the final conclusion is that we have to reject the null hypothesis since our p-value is smaller than our significance level. The machine is not filling the bags correctly. So yeah, that's all.
T-test. When testing for a population mean, the t-test can be used whenever the population standard deviation is not known. Since there is no population standard deviation, an unbiased estimator will be used instead. The formula for unbiased estimator for population standard deviation is as follows. There are three types of t-test in this chapter. First, one sample t-test. It is used for mean of one population. The second is two sample t-test. It is used to compare means of two populations and to find out if they have come from identical population. And lastly, paired t-test. It is used to compare two sets of results from one population.
Now we will look at the chi-squared test for independence. So chi-squared test is basically used to see whether or not two datasets are independent of each other. So the questions that you can expect for this type of test is to perform a test at certain significance level to see two things. Firstly, the independence of the variables, and secondly is to see whether or not there is a connection between the two variables. The key things that we have to find in solving chi-squared test related questions are observed values, expected values, and degrees of freedom. So observed values are the values that are initially given in the question. You will then need to use the observed values to find expected values. And it is also important to note that expected values must be greater than 5. If there are expected values less than 5, then you will need to combine rows and columns. If you want to see a clearer picture, let's look at the example next to it. There you can see that the expected value for folk is 4.75, which is less than 5. So what you have to do is you have to combine the rows and columns of folk and jazz. And that is how you will get the table below it, which is the table of the combined expected value for folk and jazz. And combining the expected values would also mean that you have to combine the observed values, and hence that is how these two tables are created. One is for the combined expected values of folk and jazz, and another one is the combined observed values for folk and jazz. And lastly, the degrees of freedom, which is relatively simple. All you have to do is rows minus 1 times columns minus 1. And the next step is to insert the combined observed values with any letters of your choice, which in this case we use A. And then go to your statistics test and choose the chi two-way test. And choose the observed matrix of the letter that you've chosen, which in this case is A. And then you will get all the data you need, especially the p-value, to see whether or not you should accept or reject the null hypothesis.
Last but not least, the final type of hypothesis testing is the chi-squared goodness of fit test. Keywords for this test are distribute or follow the model. This test measures the closeness of observed data and expected data, and it also determines whether a relationship exists between data and a distribution such as binomial, Poisson, and normal distribution. The investigation introduces the chi-squared goodness of fit test and draws out its links with the test for independence. When answering questions and identifying whether to use the chi-squared goodness of fit test, there are certain keywords that we should look out for. First and foremost is the keyword uniformly distributed. Here are some examples. Secondly, another keyword is the keyword consistent with the distribution. In order to carry out a chi-squared goodness of fit test, first we must define the hypothesis. Based on the questions on the bottom left, we can identify that the null hypothesis calls are evenly proportioned over the 7 days of the weeks, and the alternative hypothesis to be calls are not evenly proportioned over the 7 days of the weeks. A tip is that we can usually get the null hypothesis from the question. Now we're conducting the test. First, prepare the expected and observed value table and prepare the rejection rules. If the p-value is lower than 0.05, then reject null hypothesis, or if the p-value is lower than the significant level that we give it. Now gather all the data required and calculate using GDC. So here's how to calculate using GDC. First, create a list and spreadsheet. Second, list down the data expected and observed and name the list. Third, tab, this is the instructions on what to click. Tab, press menu, statistics, the fourth one, stat test, fourth, and GOF, which is 7 for those who are using the actual calculator, and fill all the information needed. Then find the p-value and chi-squared value, and then we can extrapolate by applying the rejection rule. This is how we can analyze our results from the chi-squared goodness of fit test. State the p-value and the chi-squared either exceed the significant level we have set or not, and reject or do not reject the null hypothesis based on our rejection rule. So for example, since p-value is equals to 0.8151, which is over 0.05, or chi-squared equals to 2.95, which is less than 12.592, we do not reject null hypothesis. Hence, there is insufficient evidence to conclude that the calls are not evenly proportioned over the 7 days of the weeks. So what we can take from this is that we should reject if there is sufficient evidence to reject the fact that it is a null hypothesis, and do not reject if there is insufficient evidence to reject the fact that it is the null hypothesis.